I'm Jack.
Jacob Cabell.
And we're Team 1.1. The goal of this project was to create a model car and test it in comparison with a car provided by the teaching assistant. In testing, we were supposed to measure drag forces as well as flow visualization patterns around the model car.
The vehicle requirements for this project included that there had to be 4 wheels, a connector on the front end, that the wheels and axles had to be able to rotate, that the vehicle itself had to be completely solid, the minimum ground clearance was 10 millimeters, the bumper-to-bumper length was 15 centimeters, the total wheel weight was 50 grams, the total load capacity 1,000 grams, and that the horizontal loading surface had to be on top of the car and halfway between the axles.
The initial plan for the project was to use a CAD software to design an aerodynamic car to test for drag. The design of the car was based on 3 criteria. The first criteria was to use the dimensions given by the TA. The second criteria was to make a design that would be simplistic enough to make by hand or to 3D print. The third criteria was to make a car that, when compared to the TA's car, we would see a major difference in drag. One of the changes that we had to make for the car was we had to remove the cylinder on the front of the car that we used for the attachment point. We had to remove this because when 3D printing, the 3D print would fail. Instead of this, we would use a paper clip with a piece of duct tape as the attachment point, as you can see in the picture here. To improve the design, after 3D printing, the wheel axles were actually rough where the axle wouldn't spin, so we had to file them down to make it smooth.
From this experiment, we learned that the geometry of an object will have a great impact on the drag force acting on it. In the model we designed, we have a rectangular cross-sectional area, which is one of the least aerodynamically efficient shape out of all the shapes we can use. From the experiment, we measured the drag coefficient for our model car to be around 1.4, and that's slightly higher than the published record of a truck, which is about 0.8 to 0.9. Our 1.4 is actually closer to a drag coefficient of a skydiver. To reduce the drag coefficient, we can fillet the corners out. That way the fluids will have an easier time passing through the car and creating a less resistance force around the car. Generally speaking, as flow velocity increases, drag force also increases. For a laminar flow, they're proportional. For a turbulent flow, drag force is proportional to the squared of velocity. From the flow visualization, we can see that in the beginning, there's a laminar flow of fluid hitting the car. Once it hits the car, it separates, and then at the end we can see it turns into a turbulent flow. And then after a while, the flow reattaches itself at the end. In the engineering industry, it is important for engineers to design cars that is aerodynamically efficient. Cars will experience drag force when they're moving. Reducing drag will help to increase the performance and conserve fuel because there will be less force required to overcome the drag force. And it will also help to improve the stability of the car.